Hello, and thank you for attending this video presentation. For the next 10 minutes, we'll tell you all about what the Mind-Controlled Wheelchair team has been up to for our multidisciplinary senior design project. We've been working on this project for the past year, and we're sorry we can't present this to you in person this year, but we hope you enjoy our compilation. So without further ado, let's get into the details. Many people take their mobility for granted. According to the CDC, 16.3% of U.S. adults have some form of physical disability, but society has adapted to ensure many of these individuals have the accessibility that they need. Even so, sometimes an electronic wheelchair is not enough. For an individual whose disability prevents them from using a joystick as well as walking, they need a new solution. That's why the mission for this team is independent mobility for everyone, and we aim to accomplish this by adapting an electric wheelchair to include a brain-computer interface that cooperates with machine vision. Hi everyone, my name is Sid Davis. I'm a fifth-year electrical engineer in the BSMS program with a graduate focus on digital systems. I'm the project manager for the team, and I've been working on communicating with the joystick that's integrated in the wheelchair, as well as communicating with the user's input device.
Hello, my name is Cheyenne Daly, and I am a computer engineering major. I have the role as facilitator on the team, and I've been working on the camera and software system.
Hi there, my name is Ryan Radicello, and I'm a computer engineering major. I've been the purchaser for the team, and I have been working on the camera and software systems.
Hi, my name is Dawson Hilk. I'm an electrical engineering major. I am the systems engineer for this project. I've mainly been tasked with working on the subsystem portions, mainly the eave stops and various mounts for the mind-controlled wheelchair.
Now, I'm sure you're wondering how to go about such an intricate problem. Well, here's where we started. Our client agreed with us that traversing an unknown area would be outside the scope of our timeline. So instead, we began by mapping an area that the user would navigate frequently. The act of navigating can be simplified to a list of decision points. We call these nodes. These can occur at intersections, doorways, and elevators, and they will require input from the user before continuing, or else a wrong turn could be taken. But let's simplify this a little more, shall we? If the wheelchair knows where it's starting and where it needs to go, then an optimal path can be created that the wheelchair simply needs to follow. This will reduce strain from the user, so instead of making a decision at every node, they only need to make two at the beginning of their journey. With this information, it's up to the wheelchair to drive itself, and the only thing the user may need to do in the middle is tell the wheelchair when to stop in the event of an emergency. To safely traverse an area once we know the path to take, we need to know if there are any obstacles in our path, as well as where the location of the next node is. Our first intention was to use Intel RealSense depth and tracking cameras for these respective tasks, and to interpret the data using a Raspberry Pi microcontroller. Unfortunately, the Pi was not as compatible as advertised by Intel, so we resorted to a new plan. We switched the Raspberry Pi out for a laptop, and as you can see, our imaging capabilities were greatly improved. Although our main issues were with compatibility between the cameras and our Raspberry Pi, the bump in processing power in the laptop was certainly useful. With our brain of the system figured out, we then focused on object recognition. When traversing a hallway, it's a good assumption to say we will not be the only people with places to be. We trained our depth camera to recognize people and objects, as well as their position relative to the camera. Using this information, we could adjust our path to make sure that we can maneuver around them, or, if not possible, then stop and wait for them to pass us before continuing. This wasn't always the most accurate algorithm, and it did struggle to find smaller objects. However, it was always able to find the object, even if it couldn't classify it correctly. Therefore, if it came across a large object in a hallway, which is more likely, it would still know to avoid it and to stop if need be, even if it sees a laptop and thinks it's a chair. Then, we used a sensor within the tracking camera called an IMU. This records the motion of the camera, and therefore, the wheelchair. Using these measurements, we could track how far we've traveled from the previous node, and in what direction. Checking this information against our internal map, the wheelchair knows how close it is to the next node, and can determine if a turn needs to be made, or if not. When we put all this information together, here's what we've got. Here you can see the general layout of the second floor of a building on the RIT campus. You can notice a variety of features that are important, such as popular locations, an elevator, and even places to avoid, like staircases, shown as gray boxes that are stacked. We mark all of these intersections that are found on the map, followed by all the popular doorways to locations that the user may want to travel to or be coming from. Then, we measure the distances between each of these landmarks, and we store it in a list within the laptop on the wheelchair. So, for example, let's say we're near the large exhibits near the north end of the building, right here. And we want to go to a different floor of the building by taking the elevator, shown here. The user would select their current location using their brain-computer interface or other input device that is best suited to their disability. Then, they would follow up by selecting their destination, in this case the elevator. With this information, the wheelchair would begin its journey. It uses the depth camera and its ability to find people and objects to make small adjustments to its path. All the while, the tracking camera is recording how far away from the next node the wheelchair is. Once the wheelchair reaches the node, it will turn towards the elevator and continue its journey. As it follows and makes adjustments to its course to ensure no harm is done to its user or their surroundings. But, in the event of a close call, we have also installed emergency stop buttons, accessible from both the front and from behind the chair. Once it reaches the elevator, the wheelchair has finished its job. The user can select a new start and end location on the new floor that they arrive, since that will likely be a new map. With the overall goal in mind, here's what we had implemented by the midpoint of the semester. Our cameras are bound together in a 3D printed model that attaches to the bottom of the wheelchair's footrest. We will use USB extension cables to connect to the laptop, which will be attached to the back of the chair. But for now, we have this test bench, which allows our software group to work independently from our hardware group, who is directly interacting with the wheelchair, whereas the software group simply needs to interact with the cameras. As for the hardware side of the project, we've been 3D printing many different mounts for the accessories that we're attaching to the wheelchair, including the structures that connect the camera to the footrest, as well as the e-stop button cases to the wheelchair's framework, as shown. In this particular design, we retrofitted an Arduino underneath the button and provided ports that will connect the Arduino to the wheelchair's joystick, as well as to the computer. There is one more design change that needs to happen to the custom PCB between the Arduino and the button, but once this is ordered and tested, this will be the device that allows the cameras to control the chair. Well, this just about catches you up to speed. We're sorry that you don't get to see our final result, but we are very proud with the work that we've been able to accomplish during the struggles brought on by the pandemic. And lastly, we'd like to acknowledge those who have helped us throughout the process. For starters, thank you to our guide, Charles Hacker, for his assistance throughout these past 2 semesters. He's helped us to generate many ideas, and his expertise in industry has helped us greatly. Next, we'd like to thank Adam Del Rosso and the NXT wheelchair team. Without the constant communication that he provided with us and his technical expertise, we definitely would not have been able to complete as much as we did. And lastly, we'd like to thank the RIT Robotics Club for providing us with a space to do our work, providing us with small resources, tools, and all the necessities for helping us to complete the project in a timely manner. And lastly, from the Mind-Controlled Wheelchair team to you, thank you for taking an interest in our project and for watching this video to the very end. We appreciate your time and always strive to simplify the lives of those around you. Thank you.